Connecting to a large language model through an API requires a few lines of code. It creates a low-barrier prototype that functions in hours. Because that initial interaction feels intelligent, architects often mistake an isolated experiment for a finished production-ready product. However, out-of-the-box models often fail when moved into live production. Without surrounding infrastructure, they cannot retrieve proprietary data or maintain consistent accuracy. They falter because a standalone model lacks ethical guardrails to prevent hallucinations and the data integration required to answer business-specific queries. Moving an AI concept to production is an orchestration problem rather than a model training problem. Enterprise AI architecture functions as a multi-layered system. It relies on interconnected databases, execution APIs, and user interface endpoints working in concert. Scaling AI for business use requires an extensive 9-step industrialization pipeline. Building the architecture to support and secure that model requires a broad engineering effort compared to the lightweight task of fine-tuning a pre-existing engine. This pipeline consists of 3 phases: establishing the foundation, designing the architecture and integration, and executing final hardening and ML ops. Mastering this blueprint provides a reliable method to move from a conceptual idea to a secure, autonomous application. Step 1 is requirement analysis. Before any code is written, architects must define strict operational bounds and specific objectives for the AI. Step 2 requires a feasibility study. Engineering teams must validate both the technical limitations and the financial viability of running the proposed system. Step 3, data collection, is the primary technical bottleneck in the pipeline. During extraction, raw data is pulled from disparate legacy systems. Warehouses like Snowflake and Databricks provide the storage layer for these high-volume repositories. Finally, processing tools clean and format this information, as neural networks require uniform data to read accurately. This ingestion pipeline acts as the circulatory system of the AI application. Without the rigorous groundwork of these first 3 steps, any downstream AI model will simply automate and accelerate the use of bad data. Step 4 is model design. Here, engineers differentiate between generalized reasoning engines and specialized execution models. Foundation LLMs, such as GPT-4, Gemini, or Claude, serve as the cognitive hub to process natural language. Surrounding that hub are custom neural networks built in PyTorch or TensorFlow, handling highly specific tasks without exhausting the central model's resources. Step 5 is integration and training. This is where modular, sensory capabilities are attached to the reasoning hub. To process speech to text, developers integrate specialized audio APIs like DeepGram. For object detection, they connect computer vision tools like Clarify or OpenCV. To produce novel media assets, they integrate generative engines like Runway and ElevenLabs. This brings us to Step 6, orchestration. A collection of powerful APIs is only useful if they can communicate with each other and with existing business software. Orchestration frameworks like LangChain act as the connective tissue. They coordinate the sensory APIs and reasoning hub, allowing the AI to route decisions directly into enterprise ERP and CRM systems. Steps 4 through 6 integrate isolated algorithms into a cohesive, multi-capable autonomous agent. Step 7 is testing and validation. Before any system can operate completely autonomously, it requires strict behavioral boundaries. Frameworks like guardrails are hard-coded into the pipeline. These enforce ethical compliance and secure data privacy before information reaches the end user. Step 8 is deployment. The model is shifted onto a production server. Containerization tools like Docker, managed by Kubernetes, allow the application to duplicate itself across cloud clusters to maintain stability during traffic surges. Step 9 is optimization, which relies on the discipline of machine learning operations, or MLOps. Live models experience model drift. As real-world user data shifts away from the original training set, the model's accuracy degrades. Continuous monitoring tools like Fiddler and Weights and Biases track this drift, retraining the system and optimizing cloud infrastructure costs on the fly. Phase 3 establishes the difference between a fragile data science experiment and a hardened enterprise system. This 9-step architecture operates as a single, unified AI-as-a-service engine. We can see its economic impact in the multi-trillion-dollar agricultural supply chain. Historically, this industry has been hampered by significant financial inefficiencies, driven by redundant intermediaries and unoptimized logistics. By deploying a fully orchestrated AI architecture, a platform named FarmScent allowed buyers to connect directly with farmers, bypassing intermediaries. The AI stack handles predictive route planning, automated warehouse management, and real-time risk assessment to make this direct connection viable. Executing this technical stack yielded a 300% profit margin lift for 200,000 farmers by removing middleman costs. Business leaders spend a lot of time determining which specific language model is the smartest. However, the underlying foundation model is becoming an interchangeable layer within the larger stack. Defensible enterprise value resides in proprietary data pipelines, custom API orchestration, and rigorous deployment practices. Companies that purchase out-of-the-box AI wrappers are highly exposed to market shifts. Those that build industrialized pipelines own their infrastructure. Engineering rigor within the AI lifecycle, rather than the raw intelligence of the model, provides the modern enterprise with its sustainable competitive advantage.